Everyone, welcome to the Taylor and McLaurin series. Okay, the objective today is to determine a Taylor or McLaurin series that represents a function. A Taylor series is defined as a representation of a function as an infinite series of other functions calculated from the values of its derivative at a single point. Okay, so it's basically representing some function as a sum of an infinite other function. So we're going to look at several examples of this, but the key here you want to look at it, we're representing a function as an infinite series of other functions. Okay. All right, so if f of x is a continuous and differentiable, if it's continuous and differentiable at x equals a, centered at a, we know the following. So here is this huge definition of a Taylor series. So the things you got to pick out is, look, you're looking at evaluating a function at a, the derivative at a, the second derivative at a, third derivative at a, fourth derivative, and so on. So you're evaluating a function and its derivatives at a specific a. You're dividing by a factorial each time, so here's the 0, 1, 2, 3, and all the way so on and so forth. And then it's x minus a raised to the n power, so 0, okay, first power, second power, third, and so on. So there's some patterns here. And so when we look at our first example, we'll see how those patterns come together. Find the Taylor series of this function ln of x at x equals 3. So the definition tells us that we need to be evaluating not only the function at a, the derivative, the second derivative, the third derivative. So I need derivatives, and I need to evaluate those. So on the left here, you'll always see me write the derivatives of f of x. So we start with the ln of x, which the derivative of that is 1 over x. The derivative of 1 over x is negative 1, x to the negative 2. The third derivative, you'd bring that 2 out front, becomes positive 2x to the negative cube. And notice how I have negative 3 times 2, x to the negative fourth. 4 times 3 times 2, x to the negative 5. Notice how I don't multiply these out, okay? Because I want to see the pattern. It looks like I'm developing a factorial here. Well, it's not only I take the derivatives, I have to evaluate whatever x is at each of those derivatives. So that's what you see on the right half here. F of 3, f prime of 3, f double prime of 3, and so on. So I'm plugging in 3 back into each of these x's all the way down. Now these are all negative powers, so I can think about reciprocal, and that's why instead of seeing 3's here, like 3 to the negative 2, 3 to the negative 3, you see 1/3, 1/3, 1/3, 1/3 to the second, third, fourth, fifth power all the way down. So these are the evaluations. Again, I did not multiply any of those out, okay, because I want to see patterns. So once I have these two things complete, I can try to write the Taylor series. So let's see, the natural log of x can be written as, there's f of 0 plus f prime of 1, which is 1/3, x minus 3, there's the center, plus, remember, f double prime was negative 1, okay, times 1/3 squared, x minus 3 squared over 2 squared, and the pattern continues. The 1/3s stay, we go up by a power, and notice how it's 2 times 1 over 3 factorial, negative 3 times negative 2, negative 1. So I'm plugging this in. This is f double prime, or triple prime. Here's the fourth derivative of 1/3. So I'm plugging those in. F of 0, f prime of 0, f prime of 1, okay? F prime of 2, or excuse me, f prime of 3 here. So I'm plugging in, these are all those derivative values, those evaluations here, okay? So now you got to see if there's a pattern. Well, I can pull out the x, the natural log of 3 here, plus, if I go from 1 to infinity, I've got 1/3 to the end, okay? So 0 term, first term, second term, third term. So it's just 1/3 to whatever term I want. And then notice how the x minus 3 comes down, and what's to whatever term I want, always divided by the same end. So look, these ends, 2, 2, 2, 3, 3, 3 match, and n over n. And to take care of the factorial, I have n minus 1. So notice I'm on the fourth term, but I'm looking at the third factorial, so I have to subtract 1 off, okay, to get the factorial. So that's how you can write ln of x as a sum of functions, an infinite sum of other functions right here, okay? Now the Mclaurin series is a center of 0, x equals 0. So again, left and right divided up, left are the derivatives. Start with your function. Derivative, 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 all the way down. Derivative of sine is cosine. Derivative of cosine is negative sine of x. Derivative of negative sine of x, negative cosine x, all the way down. Since the center is at 0, I evaluate each derivative and the original function at 0. I get these results. Sine of 0, 0. Cosine of 0, 1. Negative sine of 0, 0. Negative cosine of 0, negative 1. Okay? So pay attention. 1, 2. Some of these terms are going to drop off. So to write my series, sine of x equals, there's f of 0. F prime of 0 times x over 1 factorial f double prime of 0, x squared, 2 factorial. Now notice how I don't have the minus a like I did in example 1 because it's 0. Okay, and so 0 term, first term, second term, third term. If I simplify those out, this term goes away. The fourth term's going to away because f, the valuation of that derivative at 0 is 0. So I'm left with x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Okay, so when we write the sum, it's going to be from 0 to infinity. Every other term is negative, right? Positive, negative, positive. Next one would be negative, so we have negative 1 to the n. Okay, and so to get this, if we think of 0 power, x to the 0 power, or if n is 0, we'd get 1 here, and we'd get x here, and that's what we have. If we wanted 3, we'd have to plug in 1. Okay, so it's off by 2, so we get x to the 2n plus 1, and that's the same thing here. So to get this power at x cubed over 3, we don't just plug in 3 here. Okay, we have to make sure we get a third power there, so that would be 1 for n, and we get a 3 and a 3 here, so these two have to match. So that'll be the hardest part, getting that sum. So that's how to find a Mclaurin and a Taylor series. If you have any questions or comments, you can type them below, and we'll see you next time.